So everyone here, please put your hands up if you've used a computer. All right. Now, leave your hands up if you've used like a Linux cluster at your university, some sort of environment, yeah, dedicated for computing. Okay. Now, keep your hands up if you've used a supercomputer. Oh, wow, okay, brilliant. Okay, it looks like I can skip the first half of my talk. So thank you very much. Yeah, well, I think I am going to still cover some of the more introductory bits. Also, there's a soothing aspect of hearing something that you already know. You know that you're not missing something fundamental. But if you have any questions, don't hesitate to ask them. It's usually best to ask them within the context of the information, and so just interrupt me. All right, anyway, so I'm working at NERSC, which is a center that hosts supercomputers. And in fact, the sort of work that I'm working on involves workflows that are perhaps a little bit away from the traditional applications of a supercomputer and more looking at how do we interface computational resources with larger experiments. And I like to use this as a motivating example. So you have an experiment over on this side here, and they are collecting data in real time. And they need to have some information about that data. So it's more than just looking if the file is greater than 0, but you know, some compute needs to happen in order to know the quality of that data. So ideally what they want to do, the experimentalists over here, is they want to send the data directly to a supercomputer, have some data analysis happen here, and explore this data analysis. And based on that exploration, you make real-time decisions at the experiment. So that's sort of a motivating example. And the reason why I think this is sort of maybe a motivation for the limits of this kind of work is sometimes these experiments over here, they have a really high cadence, right? So you might get something like data acquisition, data analysis, data interpretation, needing to fit within windows that are maybe 30 minutes, maybe less. So that's sort of the challenge problem that we are slowly working towards. We are here with a lot of effort. We can do this, but I think it's also good to get other people involved in this kind of work. Anyway, so just to sketch out what these sort of workflows they tend to look like is you have data acquisition. The data, I'm going to say, magically appears on local storage. No, there's some automatic data transfer process. And at this point, you really care about how the data center is set up, right? Like, your data has arrived, and you want to have a very responsive queuing or resource management system. And the jobs running on the compute nodes, they need to give some sort of real-time feedback to the experimenters, and so that they can sometimes also work with human-in-the-loop kind of patterns, right? So you might guess some input parameters for an iterative solver here, and you're seeing the results, and you adjust your guess, and you want to resubmit, right? So the thing here is that we want to use the way that we interface with a supercomputer very efficiently. We're not going to actually learn how to set something like this up, but this is supposed to be inspirational. So essentially, if you really want to build something like a workflow that has a supercomputer in the loop, this is an example workflow for data collection at LCLS at SLAC and data processing at NERSC. And I've labeled the different sites. Here's NERSC and here's SLAC. And so you have the experiment, and data is being collected at the experiment, and data is automatically being sent to NERSC. And then at NERSC, you have a automatic workflow that is hosted on infrastructure at NERSC or possibly also at Slack that has a sense of what data has arrived, what jobs have already run or still need to be run, and what the users want. So basically in the center here you have the workflow orchestration part. It gets inputs from the users and it gets inputs from the experiment. And based on that, it submits new jobs which automatically ingest the data that they need. All right, so with this sort of aspirational thing in mind, I think this talk will actually be more about the basics, and then Björn will later start filling in more and more of the details so that you can build similar things on your own. So let's get deeper in the weeds. And I want to start with the overall structure of an HPC system, so what to expect there. And so this is now entirely based on the stuff that we have at NERSC. So just a brief question, what is NERSC? So NERSC is the Mission Compute Facility for the US Department of Energy Office of Science. And so this sets us apart from the LCFs in the sense that we don't actually get to choose our users. So our users, if they have a project funded by DOE, Office of Science, will ask the DOE, we need this amount of HPC, and the Department of Energy will say, well, folks at NERSC, here are your users. Make whatever they come with work. So this can be quite a challenge because our users have very diverse application areas. They are also diverse users themselves in the sense that most of our users are actually early career scientists, so they might not have a long background in understanding how these systems work. They come from many different countries. And so overall, I think it's a really cool environment to get some interesting HPC applications. So the data center itself is set up as follows. I have left Corey here because Corey technically is still on at the moment, but be advised that Corey is our outgoing production system and it will be shut down very soon. Perlmutter is our incoming HPC system. What I want you to take away from this slide, though, is it's not just a supercomputer, right? You need all the stuff around it to make it work, right? So, for example, everything is held together with a high-performance network. And this network gives you access to the global file systems and our long-term storage. It also gives you access to ESNet and things like DTN, so data transfer nodes and other gateways and other edge services that might make it easier to coordinate your workflows. And finally, I want to also add that there's differences in storage here, and I will cover that a bit later. But for example, there's a Scratch file system that's attached directly to the compute nodes. Maybe one more thing I want to say. You can see that we are working on the revolving basis of new machines, right? So when you develop your workflows, don't code specifically to a machine, right? Always keep in mind there's something new going to come in maybe 5 years from now, and how is this thing that I'm currently building going to work on a new machine? And just to make it even more difficult, you'll probably not know what that machine will look like. So it's not easy, but it is, I think, overall the most productive way. All right, so let's zoom into one of the nodes, one of the cabinets of Perlmutter. So we have two kinds of nodes on Perlmutter. We have GPU nodes and CPU nodes. The GPU nodes have four NVIDIA A100 GPUs and one AMD Milan, I think, CPU. And the it is Milan. And the AMD, and the CPU nodes, they have the same AMD CPUs, but two of them in lieu of the four GPUs. and here's a sort of a rendering of roughly how they're arranged. So you basically have the GPU and CPU nodes. The exterior has pretty much the same form factor. They're in these blades, and the blades are slotted into a cabinet like this. At the back, you'll have the networking, the high-speed networking, and in the front, you have access to all the coolant lines. If you ever are in our neighborhood, you should ask for a tour of the machine room floor. All right. Just wanted to also show you maybe a little bit more details about the heterogeneity of the system. So I've already mentioned GPU and CPU nodes. So here you have it in more details about, you have twice as many CPUs on the CPU nodes. And with that, you have twice as much RAM. But also the networking is important. So be aware that the GPU nodes have 4 times the networking capacity as the CPU nodes. In addition to those compute nodes, we have login nodes, which are GPU enabled. So you can develop GPU code on the login nodes. So it was really helpful if you actually write GPU code that you can actually compile. And in addition to the CPU and GPU nodes, we have large memory nodes that essentially are outfitted with even more, 1 terabyte of memory. All right, so let's drill even deeper, right? So if I opened up a GPU node, you would see, well, you wouldn't see this, but you would see schematically this setup, right? So you have your CPU that is sort of at the center of everything. It's connected to the NICs. Each NIC, so each network interconnect, is in a different NUMA domain, and this will be important later. And in addition, you are connected to 4 GPUs. Each GPU has a high-speed link to the CPU, and also NVLink interconnects between, like from GPU to GPU, so a fully connected network there. And so you can see at this point, you have a lot of heterogeneity in the hardware. And as you're designing your code, you should keep that in mind, and you should also think about, well, if I'm going to move this to another computer, what if the NUMA domains will change? What if the ratio of CPUs to GPU changes? That sort of thing. All right. So in addition to complexity in the compute nodes, you also have complexity in the file systems, right? So I like this hierarchical description on the system. You have basically high performance, low capacity, or high capacity, low performance storage, and then everything in between, right? So I think the relevant decisions you'll probably be making is, should I use Scratch or Community? And the answer is really, how much performance do you need out of your file system? I will explain in detail some of the trade-offs in the next few slides. And in addition to these file systems, I also want to point out that you have a global common and global home for storing. It's very small capacity actually, but it's mainly for storing codes and configurations and that sort of thing. All right, so it's something just to keep in mind. Our home folders are actually fairly small. So you'll actually notice that, especially if we do get to talking about Python later, you might find that you're going to run out of space. So you should really think about what you put on home, right? It shouldn't be, where you put your Conda repository, right? And the reason for that is also that this is a backed up file system. So we take daily snapshots for with a 7-day history. There's actually a longer-term backup that gets archived in our archive system, but you can browse these backups here, but you can't browse that archive, so you'd have to ask us to to restore that for your user account for you. So, when you can't fit something into home, but you still want a file system that is available to all the compute nodes, and maybe even a file system that's available to other users on the system, so then you maybe want to look at CFS. So that's a community file system. It too has backups, which I think is kind of important. And also more importantly, when you run out of space, you can actually request quota increases. You need to have a good reason, but if your reason is good enough, you're going to get your quota increase. And I want to reiterate, if you are working together as a team on a project, this is a good place to put things like shared codes, settings, some data, that sort of thing. And so then on the compute nodes, you have, well, it's not physically on, but very near the compute nodes, you have a temporary file system called Scratch. That is the biggest file system that you have access to. Once again, we are fairly generous with the quotas, and if you need even more space, ask for it, and we'll probably give you some more space. And this file system has a high performance, but it comes at a cost to the user, and that cost is we do purge it, right? So think of it as more as an extension of your RAM, rather than a place where you're going to put your 1 terabyte data set that took you 5 months to simulate, and then you've gone on vacation, you come back home, and your data's gone, right? So it's also not backed up. And then I want to just very briefly mention Cori. If in case you were using it, Cori has a burst buffer that's an on-node SSD. No, not on-node. It's just once again, it's near the nodes, but it's high-performance SSD file system. But because Perlmutter Scratch is also fully SSD now, we are discontinuing burst buffer support. And finally, once you're done with your data and you want to have a permanent place for it to live, and perhaps you also have an archive that you want other users to have access to, you can use HPSS. It's a little bit clunkier because behind the scenes, it's actually a system that runs on tapes. So don't put like a million kilobyte files in there. And we do help you. So for example, the HTAR tool is an excellent tool that will just, you point it to a directory, it will suck up all the small files, it creates a large tar blob and sends that to HPSS. And then there are cases where folks have then interfaced this system together with some web services hosted on Spin so that they can actually then share data on that archive. And we will see later, there are transfer queues that you can use for free. So you can even combine those with your job scripts to automatically collect up the data generated by simulations on Scratch and send that to HPSS, and then you don't have to worry about the purging of our Scratch system. All right. Well, now that we've sort of gone over the structure of a HPC system, in fact, I think you might be wondering, like, this is very overwhelming. So, video break. And I think this is a nice metaphor for using HPC, right? So. You might be a grad student, or you might just have started some computational work and first time on one of those systems, and you're like, God damn it. And you're trying every time. And you're just not making any progress. And I want you to know, there is hope.
But the senior people don't help much.
Oh, yeah, that's a good one. I had not even thought of that, but yes. Spot the professor.
Is it a good metaphor or not?
There's the PI. Come on, guys. Where are you? All right. So let's get started with just the really simple things. Logging in. For security, we are using a multi-factor authentication. So often you'll see something like password plus OTP. That stands for one-time password. When you log in or when you want to authenticate with the system. and you think, oh God, you have to pull out your phone or something and type in the OTP. Well, MFA keeps things safe, so it's actually good that we have it, but I understand people's frustration with having to retype passwords and OTPs all the time. So we have a tool called SSH proxy. And basically, the way it works is, or at least that's how I use it, in the morning I've got my coffee, I run SSH proxy, it'll ask me for my password plus OTP, and then once I've entered that, you get a key that has a lifetime of a day. And then you can use that key for the rest of the day, and you don't have to enter passwords anymore. If you're very crafty, you're going to use an app like Authy and password manager, and you don't even enter passwords and OTPs. You just have a button you push. There are many ways that people actually use HPC resources. So the thing that's going to be covered in this tutorial is the one where I say, well, we log in with SSH, and then we interact with Slurm. Now, obviously, you might want to use Jupyter or some other interfaces like a REST API. And so these things are going to be covered in the second half of this two-part tutorial. All right, just logging in. It's pretty straightforward if you're already used to Linux. If you're a Windows user, first Google how to use a command line interface. Now, I really recommend WSL. And so then when you are in a shell, it's fairly straightforward. It's just SSH and then username. And for Perlmutter, you have two options. You can either use sol-p1 at nurse.gov, or if you want to spell out Sol Perlmutter's last name, perlmutter-p1.nurse.gov. P1 stands for phase 1, by the way. Cori is pretty much the same approach, but remember, Cori is going to go down soon. Now, if you are running tools that require a GUI, the first way that you can run these tools is simply by SSH-y and then the usual SSH command. That will enable X forwarding on your machine. And so once you've logged in, you should see our end user license agreement, essentially some stuff about Perlmutter, and then at the very bottom, you'll see, for outages go here. By the way, if you can't log in, do check our outage page. So maybe there's a outage, maybe there's a scheduled maintenance. But if you land on a logger node, then that's great. You can actually submit jobs, interact with the HPC system via SSH. By the way, interrupt me at any time if you've got questions. I'm not offended. The other way you might want to start an X session is not using X. So you can imagine what X actually does is you have your application running in the on one of the logger nodes in the background here, and that application will forward all the GUI elements, pretty much all the X widgets and data that you need to render a window. A really typical example for why this might be wasteful is, let's say I want to visualize those particles in an MD simulation. We have 1 billion particles. Well, if you render 1 billion particles in X, it will send 1 billion dots, even though your screen can't display 1 billion dots. So much better is to start the X server on Nurse side, have a much higher bandwidth connection with the logger node or compute node here, and then just forward the bit the visible part of the screen. So we use No Machine for that. By the way, this has the additional advantage that if your X window connection gets interrupted, this application crashes. Whereas if this connection here gets interrupted, your X session remains. It takes a little bit of setting up initially. That's why I recommend, if you do want to set up No Machine, go to our docs pages and look at the NX section here. and just follow those instructions to set up no machine. And yeah, once it's properly set up, you'll get a login screen over here, and click on like a Linux session here, and it will show you a window of the X session running at NERSC, and you can then log into our systems. And this then automatically, like these shell sessions then do the usual X forwarding automatically. All right, more videos. Oh no, the ducks haven't made it so far. Well, I guess we'll have to check in later. But, I thought, okay, I think we were talking too long. Progressively, you'll see them make progress. Well, let's move on, I think. Oh, yeah, okay. All right, so maybe you feel like you're at the bottom step and you're about to go on to the next step up, right? So the next step would be running jobs. Just wanted to maybe elaborate on some language here. So you might see language around jobs, processes, and threads. So a job is something that's sort of unique to HPC. It's actually unique to the scheduling system that we use. So a job really defines a set of tasks that you want to do. You submit that to the job scheduler. We are using Slurm, and the most common way you interface with that would be to write a short script, and that script has all the information Slurm needs to schedule your job within the resources. So the job will then launch the processes. So a process is, you really should think of it as an instance of your program. It has its own memory space, and so if you do have programs, you do need to explicitly if you do have processes within one program, you do need to explicitly transfer data between each process because they live in their own memory space. However, you could even go a little bit more bare bones and use threads. So threads are pretty much like processes, but they share memory space. So these are very commonly used for breaking up tasks within a node. Tasks like matrix multiply or something, where you have a large algorithm and you can break that algorithm up into individual subtasks, and then each task will work on shared data to achieve the algorithm. And it's really important, I want to elaborate a little bit that this kind of parallelism, that can't scale between nodes, right? So you really should think of it as this is many nodes orchestrated. This is how we run programs across several nodes, and that will handle communications. And this is how we parallelize work within a node. By the way, OpenMP is a very common way of achieving multi-threading, and that's why you might also see OMP num threads. And if you're using NumPy or SciPy, behind the scenes it will be using BLAS, and there you have other environment variables that will actually adjust the amount of threads that are available for those libraries. I mentioned data sharing, and this is, I think, an important fact. Threads can cause race conditions, so you have to be very careful when you program them. Processes need to explicitly share data. You can use a library like MPI or sockets for that, but in that case, while you don't accidentally generate race conditions, you have to remember to send and receive data with those. And jobs themselves are really almost independent, right? So if I want to communicate a state between two jobs, then I need to either write some data to a disk. This can be rather slow. If you want to avoid problems of shared files, like multiple jobs clashing and causing a race condition again with the same file, I recommend you use some dedicated service like a database. So I already mentioned like a process is tied to a single node, and a thread is tied to a core. So if you imagine a modern CPU, that CPU has multiple cores, and often those cores have maybe 2 or more hardware threads, and so the threads themselves are actually tied to a physical core. Sure.
Is that actually true? Because my impression is that Perlmutter specifically seems to have some trouble with its CPU pinning, and this goes back to Slurm. So where is this fixed?
Okay, I think I've gotten the right slide.
This would be exactly how a computer should work, right?
Yes.
So one of the interesting aspects of Perlmutter is that it doesn't do that.
I want to paraphrase you. One of the interesting aspects of Perlmutter is that it, in many aspects, is broken.
Yeah, no, I know. Yes. I'm not trying to.
No, but that's true. There are Perlmutter is actually the first of its generation in terms of networking and software stack, and I want to say this is when things work, right? So I want to say that Slurm is responsible for placing the thread on the core. Actually, it's your operating system. If you're running a multi-threaded program on your laptop, your operating system's task scheduler would, if you use something like HWLock or some way of communicating with your operating system, you would pin your thread to a core. If you don't do that, then it's sort of Wild West, right? Like there's a scheduler running in the background. It decides this core is free, this task goes there now. But that comes with additional overhead. So for an HPC setting, we want to avoid that. And that's why we usually advise people to use Slurm to pin your threads when it works. All right? That's the intention, yes. I'm not aware if it's been fixed yet. But there are many such issues with new HPC environments. And we're working actively with HPE, and they are working behind the scenes to fix these things, and they will be fixed eventually. All right. Anyway, so I wanted to just illustrate that this is an important distinction to remember. So Slurm is there for placing your program on the resources, right? And everything else is your job, right? So for example, if you are deploying an MPI program, your job is to then set up the code that communicates data between processes, or the code that has using a multi-threaded algorithm to solve a problem. So let's look at some ways of using Slurm to actually manage our resources. By the way, I want to reiterate that. So we are going to be looking at job scripts. That's not the only way you can interact with Slurm. And so later, I think Björn will be talking about the Superfacility API. That's a completely different way of doing it. But essentially, it's the same thing. You're still talking to a job scheduler and a resource manager, and you're asking for certain resources. All right, so the way that you can talk to Slurm from your SSH session is you can either say sbatch and then my job script, so that would be a file here, or you could say, well, actually, I want to interactively work with a compute node, so instead you can run salloc, and then whichever options that you would have put in the job script, you can put directly to salloc. So an example here is if I wanted one node for 5 minutes, and so I've got salloc-1, I have a CPU node, it's going to run for 5 minutes, and it's going to charge that compute time to the following project. It's going to use a debug queue. Oh yeah, and if you get stuck, Iris, which is that page where you set up your account, has a JavaScript generator. So there you can also get like starting point for your JavaScript by just selecting different things you want. The way it really works is when you're on a login node, you might run salloc or sbatch, and that puts you onto the head node of that job. Right, so in this case, you've got 1, 2, 3, 4, 5 nodes. So let's say you ask for 5 nodes, you would get a setup like this. And then from the head node, it would launch, usually with the srun command, the multiprocess code, right? So it's probably an MPI code that you're running. So the srun is taking place of the MPI run. Sure.
Just to the previous slide. Let's say I now I ask for large allocation and I want to do a series of smaller calculations within this.
Right.
I would run multiple srun commands.
Right.
Is it something that you as a computing center are happy with, or is it something where I'm more misusing it? And like, it would be great if like all my codes would accept external MPI communicators.
Right.
They don't do it yet.
All right. We have to work on a project. No, I agree that it's a little bit like, you get given a box and now you have to sort of fit something into this rectangular box and like nodes and time. And it can be very frustrating. As a center, to answer your first question, as a center, sure, you can put multiple srun commands within a job, right? So let's say, you wanted a 3-node job and a 2-node job. So you do one srun that will like grab these 3, and then a second srun would like grab these 2, right? So just
about like multiple hundreds of srun commands in one allocation. So like I have DFT calculation. Each
right.
DFT calculation goes on one node, and then I do several thousand DFT calculations in one larger allocation.
Right. That's fine too in principle, but at some point you are running into the technical limitations of the assumptions that Slurm has about these things. I don't know about, did you say 1,000 or multiple hundred? Yeah. At some point it makes sense to use like a workflow management tool that will sort of sits between the resource manager like Slurm and your workflow. And those tools will also have the capability of repackaging your individual jobs into larger chunks that then the resource manager is more optimized to deal with. And we should talk later about what's the right workflow management tool for you, because there's a massive ecosystem out there for those, and each one has their own advantages and disadvantages. Long term, I think would be great if you can just give me the MCOM world or MPI-COM world or something like that, and just allow us to, here's a pool of resources, we want to just divide them up, but we're not there yet. I'm sorry. The other option, by the way, is if you don't really care about highly optimized network traffic, is you can break it up into many small jobs and use the backfill scheduler. And the other approach, if you care about, moderately fast but still not like MPI level fast communication, is you could not use srun at all and rather start something like Condor or another service, like another resource manager within Slurm, within that job, and then use TCP over the high-speed network. I think you were a millisecond faster.
I just wanted to briefly comment because we talked about this morning. So to say something good about Perlmutter 2 in spring when it was still in testing, right?
Yeah.
And it actually worked. We managed to do this with an MPI communicator on Slurm when there was no bookkeeping. I didn't know how much time we were actually going to use, but it works. You can do 8,000 DFT calculations of 300 atoms each from full relaxation.
But were these like separate Slurm commands, or were?
No. This was 8 separate jobs, one srun command each with an MPI communicator that split.
Oh, cool.
So this is amazing. It actually worked.
Right.
And, we didn't really trumpet it very widely.
Right.
Maybe we should have, right? But you can use this thing for massively parallel
Yeah.
DFT calculations that are in themselves non-trivial.
Right.
Yeah. So once it comes back to life, right? Once these little issues now are fixed, I think it's going to be great.
No, was this before we switched from Slingshot 10 to Slingshot 11?
So it was in March, maybe.
Okay.
And the real maintenance that caused us trouble was October 4th, October 5th. I think there was a big maintenance on October 5th. Right. That was an interesting maintenance.
All right, maybe you should talk later. This is all interesting.
It's a great machine when it works. That's what I'm saying.
Yeah. Anyway.
Yeah, I'm just wondering, do you support job arrays for Slurm? And
Yes.
would that be maybe a one way of doing what we just talked about, so large numbers of jobs
Yes.
Without having just one
Yes.
job, but just packing them in arrays, right?
Yes.
It gives Slurm more capability of managing
Yes.
the workflow, right?
I have an example of that later, but yeah. So there is a lot of like in principle, I would say if you don't have any communication between the jobs, break them up. Of course, then some people want to optimize wait times and like overall throughput. And so then there's different strategies about how much do I bundle them to get slightly bigger jobs, but then maybe higher throughput. And Slurm does come with dependencies and job arrays that really make this breaking up much easier. Yeah.
For the job arrays, if I understood them correctly, they are just like S1 command. It's just like calling multiple S1 commands in the background, right?
No, this job arrays are, it's more like an accounting trick. So you can tell Slurm, I mean, yeah, like you would only have one srun command, but Slurm implements it as many different jobs that are then in the
end, it's the same call. It's
yes,
just like,
it's the same call.
It's more clean in the syntax, but like it's still like I'm not sure if I fully understand this. Like, how much does srun communicate to the central scheduler if I just distribute resources within my allocation?
srun doesn't communicate with the scheduler. So once you're here, right? So when you run sbatch, you are asking the scheduler for resources. Now you've got the resources. It's one blob of resource, right? It's literally a rectangle. You've got time and number of nodes. At this point, srun knows what nodes have been assigned to your job and other resources. And then srun, now the question that you're probably asking is, what if I run several sruns? How do they divide things up? And that's sort of a first come, first serve thing.
What I can control, right? So I can control like how many nodes I want. But my understanding was always that srun still goes back to the main schedule, and that's why it's not recommended to do like thousands of srun calls if I just have small tasks in between. So I have a framework in place to generate these calls.
I see what you mean. Yeah, so there is srun does need to know what else is already running on these nodes. And that is not that's not optimized for that kind of application. Yes. All right. Yeah. So by the way, that's why I meant if you don't need to talk, just make it several sbatch, right? Like make it several separate jobs. Right.
But then, like NERSC has limitations. I guess how many jobs can I submit? 1,000 or 300?
You can submit a lot of them, but only 2 of them accrue priority.
Okay.
But if the jobs are small, the backfill scheduler is very likely to pick them up.
Yeah, but still, it's kind of it's not really deterministic. So the job arrays is kind of just like this. It's many jobs similar. It will kind of then we have some mechanism in place that will kind of try to put them together in like one block. But then they kind of get scheduled faster.
But then in the background you do the same, right? So
we put tricks in it so that to get like if you really just have like a bunch of jobs that are the same, we try to get them through faster to make high throughput. But really, if you're just going for like what your applications or your workflows kind of is called back off task, it's very common for workflow managers. So I would say go and use a workflow manager for this. Get a large block and get your job cycled through by another mechanism, and not do srun. And because every time srun runs, it makes a transaction with Slurm. It will talk to the database. And there's like a rate limit on how much Slurm can support. And that's why specifically it's terrible for like a lot of nodes, which we have at Corey. And that's why in the docs there's this section where we say, please don't run like thousands of sruns, because it will essentially bog down Slurm, because we're just trying to process your sruns and trying to hook them against the database. That's not really efficient.
I'm really interested, like, which workflow images you would recommend, because like what I see in the background, that many of these in the end still call srun, and they just give me a nicer syntax to not write the srun calls myself.
That's true. There's a lot of workflows out there who sit on top of the schedulers, but you want something that sits inside, that can actually run inside an allocation, like Parcel or Task Farmer, one of those.
Also use the S1.
Well, it depends on how you configure it.
Okay.
So
And so I'm definitely curious to learn more in this detailed level of like how to, the one application is fitting machine learning potentials and like doing this in active learning workflow where I have thousands of DFT calculations. In the beginning, I don't know how many I will have. And I need the result of the DFT calculations in between to make the next test runs and see, okay, where do my potentials fail, and get new structures and add them to the DFT pool.
So there.
There's actually like an example for Parcel to do
Yeah.
this.
Yeah, Parcel it has a. So I don't know if you're gonna cover workflow managers.
I mean, if we can talk in the break, we can try to whip up some slides for tomorrow to cover it.
That would be great.
Yeah, it sounds really interesting.
Okay.
I had no idea that this slide would cost this. But yeah, no, I love this discussion. I'm gonna move on, but please also let's discuss in the breaks. So because these are really interesting problems. Anyway, so I was going to now look at the anatomy of one of these. Can you all see? I think so. Yeah. So this is the anatomy of just a regular bash script. And I think the important thing that I think most of you already actually understand, so maybe I will skip over this, is you basically ask for your resources using this preamble here, and this would be pretty much the same parameters you could pass to salloc, and then from within here, within the head node, you would then run the srun. By the way, there's a short and a long form syntax. So you might already have, I think most people are more familiar with the short form syntax, but then there's a more descriptive syntax that sort of maps onto this short form and actually extends it. Oh yeah, so just very, very briefly, yeah. Anyway. It's literally a bash script. So you could actually run this. You've got the preamble and, oh yeah, I wanted to point out, you have a setup phase. So often you will also see a lot of jobs will configure their environment, and that's how it talks to libraries and frameworks. Yes?
Sorry to make something that is probably a personal comment, but it is, and we never talk about these scripts, but it's great to see them. I think one really important thing, at least at NERSC, would be to have a module list in this particular script. So the reason is that the default modules change, but the changes are not announced.
Right.
They can change from working versions to non-working versions.
Right.
And most users are unaware that even if they compile with a particular compiler against a particular library version, then in the Slurm script, everything is different.
Right.
And could be different tomorrow.
Right.
That's the problem, right? Without any knowledge.
Right.
So putting a module list here, even in the simplest examples, would be extremely good.
Yes.
Then you can trace.
So just for folks on Zoom, if I put in a what is that? Here we go. If I put in the command module list in here, then your job log will show this is the modules that were loaded at the time of my job. And yes, that's a very good point. The default versions will change. So if you go with something like module load Python, the Python version might change. Now there's a way to guard against that, right? Because I could have, before every job, I could have module load Python /3.9 and all the libraries that I want to use, like, if I want to have a specific lib fabric, right, I could put the version there. That has the advantage that it won't secretly change on you. Of course, the disadvantage is if you discontinue an older version, your jobs will break. But at least then, you'll see it, right? Like a job ran for a second and broke. What happened there? So yeah, those are two kinds of strategies in this situation. All right. Okay, so now let's go we're still actually going deeper and deeper. So let's understand one of these job scripts and see how this interacts with MPI. And we were talking about thread pinning as well. So this is an example of 22 MPI tasks per node. So one way of specifying tasks per nodes is I'm going to say how many nodes I want. I want 40 nodes here. And then I'm going to say how many MPI ranks. By the way, Slurm calls it tasks and MPI calls it ranks. I would have 1,280 MPI ranks spread out over 40 nodes. That's 32 MPI ranks spread out over per node, spread out over those 40 nodes. Now these nodes have hardware threads available. So you can use -C and give each MPI rank 2 hardware threads. And then you can say --CPU bind and set that to cores. And that, when it works, will make the threads for each rank be bound to a core. Did I say this? Yeah, okay. And now if you want to use OpenMP together with MPI, so here is the same example, but, this is MPI code, but we are now spreading it with 4 MPI tasks per node, but then we are using 8 OpenMP threads per MPI rank. And then once again, you need to use core binding, but now you need to make sure you are assigning 16 hardware threads, so that's because there's 2 hardware threads per core, so that's 8 cores here per MPI rank. All right, did I cover everything here? All right. So yeah, this is I just wanted to give you an example for a GPU node, and this might be hard to see. I will maybe elaborate a little bit. So to use a GPU node, you use the -C or -- constraint GPU. Now this is the long form syntax that the short form doesn't have, which is kind of, I like this, where you can say number of tasks per node, right? So now I don't have to worry about -C anymore because I have 64 tasks per node. So then I will say 2 CPUs per task, and then I set 4 GPUs per node. And so this is enough information for Slurm to launch your job. What else did I want? Oh yeah, and so this is the CPU version. You of course you drop the GPUs per node request, and then you set the CPU constraint. The CPU nodes have 2 CPUs per node, so you can set twice as many tasks per node. Right. Okay, so this is just reiterating the fact that really do use CPU bind, set that to cores, and then specify the -C to set the thread affinity correctly. And also, this isn't so much an issue with the Milan nodes, but so with the CPU and the GPU nodes on Perlmutter. But this used to be a thing on Cori, and depending on your application, it sometimes makes sense to leave a few cores unused, just so that your operating system has some resources to run in the background and not get in the way of your application. There's lots more information, by the way, that I'm not going into here, and so I suggest checking out our docs pages on Affinity, and that's actually enough reading material for an evening. Question?
Yes.
Hi.
Yeah, so the GPU affinity is interesting, right? Because you ideally like your GPU to be tied to the MPI tasks that are in the same NUMA domain.
Yes.
And so is that controllable?
Yes. I think I have a... I'm going to skip... Oh, yeah, I wanted to skip to this slide. Here we go. You can use GPU bind closest, and that will bind... do I have an example? I don't know. Okay, so there's an environment variable, I haven't written it down here, called CUDA visible devices. And by the way, it's actually helpful to echo that and then just see go into an interactive node and play around with srun with different parameters and echo CUDA visible devices, and then you will see what your device, how your devices are associated with your Slurm tasks. If you set GPU bind closest, it will put the CUDA visible devices array should just be one number, and it will be whatever device. It will always be 0, by the way. But if you then looked at the device ID, it will be whatever device is in the same NUMA domain as that task. And I think that was the point of the slide as well. Oh yes, actually I can show you an example of that. Up here, you're launching. You should be able to see here. You've got 8 tasks. And you're only binding threads to cores, you're not binding GPUs. And then what you see is, you'll see this a lot, MPI will print out of sequence. So rank 0 has this device ID, rank 1 has this device ID, rank 2 has this device ID over here. So you're going round robin around the GPUs. And that means that depending on what this binding is up here, you might not be in the same NUMA domain. If I do the same thing, but this time add GPU bind closest, and just to remind you, these are the thread IDs and the cores. So you can see here that rank 1 here and rank 5 here have the same device ID. And then if I look at 1 and 5, they fall within the same NUMA domain. And if you did this with the other examples here, I mean, this is sort of truncated, but you'll see that you land in the same NUMA domains. And yeah, I actually already mentioned that it's really helpful when you don't want to know what these flags all mean. Just grab an interactive node, and you can use the interactive queue to get a node within 6 minutes, and just experiment with the different flags. And we have some sample programs that print out the NUMA domains and the device IDs, and just make sure that things are what you expect them to be. And once again, you can look up the documentation. All right, more ducks. All right, so some more ducks have gotten further. All right, so yeah, couple more minutes. Let's go into some more advanced uses of the queues. First, we have the shared QoS. So by just setting queue to shared means that your job will run on a queue with other jobs. And so that's really when you have a task, when you've got a program that can't make full use of a queue, of a node, and you want to let other jobs onto the same node, and you don't want to be charged for the full use of that node. So submitting to shared helps. Just be aware, though, that you also share memory. So if there's a task in there that uses a lot of memory and you want to use a lot of memory, you might run out of memory. Now, another thing that's really helpful, especially for that earlier example where you had to have highly responsive jobs, is preemptible jobs. So this is the other side of that. Like, let's imagine you have urgent jobs and less urgent jobs. Well, you might say, well, my jobs are less urgent, right? So I'm going to mark them as preemptible. And there might be 2 reasons why you want to do that. One is, there's some, that we haven't really settled on what kind of discount there ought to be for preemptible jobs, but in the future there will be some discounts for those. But also maybe your job needs to run for a very, very long time. So it doesn't fit into the queue. So what you want to do is you want to run this preemptible job. It will run until the maximum time that it can run. It gets preempted, so it will save its current state, and then it gets resubmitted, and you basically make incremental progress that way. So the way that preemption works is you can tell it how long you want it to run in total, and you tell it what signal to be sent during preemption. And if either a higher priority job comes in, or you run out of the queue max wall time, your application gets sent sig user 1, and it has 60 seconds. You can actually adjust this variable here. It has this many seconds to intercept that signal and do something with it. So for example, save its data and quit gracefully. If it hasn't quit after receiving user 1 after 60 seconds, Slurm kills it. If you want some examples of how to intercept these signals and save your data, look at some of these checkpoint examples. Oh, and this job will then automatically requeue. Sure.
This preempt queue, because this sounds like a good use case for a lot of people doing large-scale molecular dynamics simulations, where typically, because you need to accrue a lot of simulation time, it's routine for people to run back-to-back what do you call it, checkpointing. We call restart lamps. So typically, you try to get a 24-hour slot, you run it, and then you have another job in the queue that's waiting for the next 24 hours. Yeah. Would this allow you to get 24 hours in a kind of a discontinuous manner? Is that the idea?
No, this one actually gives you 96 hours in a discontinuous manner. But yes, exactly. So what this will do is will automatically requeue. And you have to write your application to, so you can use DMTCP or MANA or framework like that to do automatic checkpointing and restart, or you do it manually yourself. But so your application has to support checkpoint restart. But when it does, you can just use this job script, so these flags in the job script header to get those. This one time it's 24-hour chunks that will eventually fill out 96 hours.
So is there an incentive for somebody to use that queue over the regular queue?
Well, this is 96 hours is too big for the regular queue wall time limit.
Yeah, but I mean, people can still chunk it up in a 24-hour block.
Yeah, they can manually do it themselves. That's true.
We don't allow 24 hours, only 12.
Oh, sorry, I said. Right.
So now 24 hours is for the preempt queue.
Right.
We had it for free for a long time.
So
very reduced.
I guess what I'm getting at is the only thing people care about ultimately is, say their job needs to run for 1 week of total simulation time, right?
Right.
And they want to know, okay, is this 1 week going to take me 1 month to accomplish, or is it going to take me 6 months to accomplish?
Absolutely.
So is there an incentive then for people to use this preempt queue, which in the short term, I guess, will slow them down, but maybe it'll actually benefit them over the longer term?
I think that's that depends on a lot of the conditions. There's another thing that I mean, for example, there's a queue that has a charge factor of 0 that also is preempted. So we are thinking about different ways of discounting preemptible jobs. So that might not be you get your result faster, but you get more result in the long term. The question, I think, comes down to how much time does this restarting and checkpointing take? If it's next to no time, then shorter chunks with higher priority will get you through the queue faster. But if it does take a long time to checkpoint and restart, then you do want to minimize the number of chunks. And then you might want a queue that gives you bigger wall time. All right. And I just wanted to point out, as mentioned earlier, you have the transfer queue, and you can actually put this line at the end of your bash script, which would then automatically submit to the exfer queue the HSI put command, and then moves that large file that you've just simulated to HPSS, so that you don't have to worry about the scratch purge.
I would like to add to the preempt queue only costs a quarter.
Oh yes, it's discounted.
Quarter. That is like the charge factor is a quarter for the preempt
nice.
queue.
I didn't put it here. Yeah, there's a discount for this queue.
That's a nice discount.
Look it up on our docs page. It always has the most recent information. If you want a big queue, as we speak about it, it might have already been changed, but just look it up on our docs page. Oh, that's the most recent charge factor.
How did you come upon 25% as the magic discount?
We have a committee to determine these charge factors. We have very active engagements across entire NERSC. We type in like working groups, and this working group decides charge factors and how many and all the limits, and it's broad participation from many stakeholders in NERSC.
Yeah, and of course, I guess you have to look at to what extent people are using it, right? Have you noticed, like, is it popular to use the preempt queue or not?
Oh, I think I don't know what the last analysis is, but it's monitored constantly.
Yeah.
We monitor the queues and we make decisions based on the repair center. So yeah, I think for the individual user, it will always come out, well, I want to have this application and it doesn't really work for me, but we have 7,000 users, so we have to balance all these different interests.
Yeah.
If you form a big enough lobby that wants to say.
Well, not just lobbying, we do like to hear from our users. And,
right, yeah. So if it's a specific use case, that's
yeah. And the thing is, if you tell us, S1 is broken, of course, that's going to be really high priority. But the point is, like, if you tell us information, we're going to act on it. It might not seem like we are, because there might be other competing interests. But we do still like to hear. Anyway, as also mentioned, I've already talked about different queues, and we've already talked about job bundling, so we've sort of front-loaded our discussion. So by the way, just very briefly, if you have multiple S-runs, don't forget your ampersands and your weight. I briefly mentioned this. Here's the example of job chaining. And there's really two kinds of chains that you really need to worry about. One is a chain that can break, and another is a chain that just continues regardless. So by essentially what you do is these commands in the brackets, they return the job ID. So I'm going to submit my first job, I get the job ID out, and then when I submit the next job, I say, after that job is quit in the OK state, and then given the previous job ID, I can submit the second one, and then for the second, submit the third and the fourth. And so this way you create a chain, and if let's say this job here, job 2, does not end in the OK state, job 3 and 4 won't start. You can use after any to start it regardless. And you can also add the dependency after OK or after any to the job script. And finally, we also had mentioned job arrays. So that's just a way of using a single job script, and then Slurm will fill in, for example, the Slurm array job ID. And we also mentioned this. It depends on what threshold, right? Thousands, yes, please don't do that. I don't actually know at what level it's acceptable. I tend to use a workflow engine for most of my work anyway, so so we've discussed this also. And then finally, I also want to give a brief mention of multi-process service. So you can use the CUDA MPS control daemon to start and stop MPS, and that way it allows the sharing of a GPU between different MPI ranks, and so technically you can already share it, but this improves the performance when you have independent processes that share the same GPU. All right, and I think this is actually getting close to the end of this talk. I just wanted to say you might find a HPC system a bit unstable, and this is, I think, a good illustration why. Because you have many users that they are trying to act in good faith, right? They're trying to stabilize this thing, but it does sometimes just result in a situation that is difficult to stabilize. And so there's more material, but I think, how much time do we have? I think I'll maybe just stop here and let Björn pick up the stuff that I didn't get to. And yeah, with that, I thank you for your attention.